So in the group theory course that I'm currently teaching, we're going to do a little section on matrix groups. And that's going to include matrix groups and then the so-called Euclidean group in a following video. And so of course, matrix groups could be a whole course on their own. So this is not going to cover much. But in the end, we'll be able to classify all possible wallpaper patterns. That's kind of our end goal, with a bit of a focus in this first video of looking at matrix groups over finite fields, because I think that's kind of interesting. So anyway, let's get this started with the definition of a field. So a field is a set which we'll call F together with two operations, addition and multiplication, so that if you take F with addition, you get an abelian group. And then if you take F and remove what I'll call 0, which is the additive identity, you get an abelian group if the operation is multiplication. And then, well, there's going to be one more axiom. Of course, there are several axioms built into this first line, but the additional axiom will be the so-called distributive rule. So for all A, B, C, and F, we have A multiplied into B plus C is AB plus AC. Okay, so anyway, now we've got that taken care of, we can define the general and special linear groups. And so those will be GLNF and SLNF. So GLNF is going to be all n by n matrices with entries in the field so that their determinant is non-zero. And that ensures that we get all of the invertible matrices. And then SLNF will be the members of GLNF so that the determinant is 1. Okay, so let's look at an example. And so the example we'll look at first is GL2Z2. So what is this? This is going to be all 2 by 2 matrices, so A, B, C, D, where A, B, C, and D are elements of Z2. And then we know that AD minus BC is equal to or not equal to 0. So needless to say, we should talk a little bit about some finite fields here, since we're going to be doing some matrices over finite fields. And, well, since this isn't a course that is looking at fields super carefully, we'll just say very, very quickly that a nice example of a finite field will be ZP. Observe that it satisfies all of these conditions here. Okay, so anyway, let's get into this. So this shouldn't be too hard to simply write all of the elements down, given that we've got two restrictions making this thing pretty small. The fact that we're in Z2, which means we only have elements 0 and 1 for the entries, and then we've got 2 by 2 matrices here. So in the end, if we were able to let A, B, C, or D be anything from Z2, we would have 16 elements. But of course, since the determinant is non-zero, that means that we'll, in the end, have, well, fewer elements. Okay, so let's get these written down. So we've got first the identity matrix. And then next, we've got this matrix 1, 1, 0, 1, like that. I'm going to read these row-wise. Next, the matrix 1, 0, 1, 1. So there are 3 matrices. And then we've got this thing which has 0 on the diagonal and 1 on the off diagonal. And then we've got this matrix 1, 1, 1, 0. And then there's one more. And that's the matrix 0, 1, 1, 1. And maybe before we analyze this group a little bit more, I'd like to observe that GL2Z2 is the same thing as SL2Z2. And that's because the determinant being non-zero in Z2 is the same thing as saying that the determinant is equal to 1, given that Z2 only has 2 elements. And now I'd like to observe the following, and that is that this is a group of 6 elements that's non-abelian, and we can check that it's non-abelian like this. If we take the matrix 1, 1, 0, 1 and multiply it into the matrix 1, 0, 1, 1, what will we get? Well, doing standard rules of matrix multiplication, it's pretty easy to see that you get the matrix 0, 1, 1, 1. Again, notice that this first entry right here comes from multiplying 1, 1 into 1, 1 here, so you get 1 plus 1, which is 2, which is 0. But now let's compare that to the product in the other order. So let's see, we've got 1, 0, 1, 1 multiplied into 1, 1, 0, 1. So what will we get in this case? So now we're going to get a 1 in this first entry. We'll get a 1 in this entry right here. We'll get a 1 here and a 0 here. But observe that these are not equal. So what does that tell us? Well, we know GL2Z2 is a non-abelian group of order 6. But there's only two groups of order 6, and only one of them is non-abelian, and that is S3. So that means that GL2Z2 must in fact be isomorphic to S3, which itself is isomorphic to D3. Now let's maybe recall while we're at it that any non-abelian group of order 2p is isomorphic to dp. And here I'm using the notation that p is prime. So that's something that's fairly straightforward to prove. If you look at my abstract algebra playlist, we prove that in the abstract algebra playlist. So now, well, this shows that it's isomorphic. If you wanted to find maybe an explicit isomorphism, you'd have to look for an element of order 2, and you'd have to look for an element of order 3. So let's observe that the element of order 2 looks like that. Well, there are actually going to be 3 elements of order 2, but there's one of them. You can pretty easily check that if you square that, you get the identity. So we would perhaps send that to S, or perhaps to 1, 2, the transposition, depending on if we're trying to go to S3 or D3. And then we need an element of order 3. And you can check that this matrix 1, 1, 1, 0 is a matrix of order 3. And so now you would need to send that to an element of order 3. And so that could be sent to R, the generating rotation of D3, or the 3-cycle 1, 2, 3, if you wanted to go into S3. So those would build your explicit isomorphisms. Okay, so now let's see what we can do from this. Okay, the first result we're going to look at has to do with the order of GLNZP and SLNZP. And so we'll show that the order of GLNZP is p to the n minus 1 times p to the n minus p times p to the n minus p squared, producted all the way up to p to the n minus p to the n minus 1. And then the order of SLNZP is actually the order of GLN divided by p minus 1. But after doing some cancellation, you get the following product. So we've got p to the n minus 1, and then p to the n minus 1, p to the n minus p, all the way down p to the n minus p to the n minus 2. Okay, so let's prove the first result first, the order of GLNZP. And so let's consider a matrix. And well, of course, our matrix is going to be inside of GLNZP. So let's maybe write it like this. So we've got A11, and then A12, all the way down A1n, and then here we have A21, A22, all the way down A2n. Then all the way down here, we're going to have AN1, AN2, all the way across ANN. So we are assuming that this matrix is an element of GLNZP. Okay, nice. And now we simply do a counting argument on what the possibilities are for each of these columns, counting from the left. So if we look at this first column, so if we're building our matrix starting at the first column, well, so this first column can be anything except for the 0 vector. And so I'll just write 0 with an overline for the 0 vector. So how many possibilities does that leave us? Well, let's observe that we've got n entries here, and each of those entries can take on p different values because we're in ZP. So in the end, we've got p times p all the way up n times, so p to the n possibilities for our entries. except we can't have the 0 vector, so that takes away one possibility. So in the end, we have p to the n minus 1 choices for this first column. And now let's move down to this second column. And let's observe that this can be anything except a multiple of column 1. So again, we're going to start with p to the n possibilities, just because we can take anything from zp to any of those entries. And now we're going to subtract off all of the multiples of column 1. But how many multiples are there of column 1? Well, there are going to be exactly p multiples of column 1, given that we're in zp. And now we essentially play the same game over and over and over again. So let's maybe move down one. So let's move down here to the third column. And let's observe this can be anything except a linear combination of column 1 and column 2. So in other words, let's spell this out. V3 cannot be equal to C1 times V1 plus C2 times V2. But how many choices are there for linear combinations of column 1 and column 2? Well, let's observe that since we're in ZP, there are P choices for each of these entries. So that means that there are exactly P times P or P squared linear combinations of column 1 and column 2. Now, starting with our starting point of P to the n possibilities for the entries, we subtract off P squared for the number of linear combinations of column 1 and column 2. And now I think you can probably see where this goes. So if we are in the kth column, the kth column can be anything except for a linear combination of the previous k minus 1 columns. But there are going to be exactly p to the k minus 1 linear combinations of the previous columns. So in the end, for the kth column, you will have p to the n minus p to the k minus 1 total choices for that kth column. So now putting this all together, you get the order of GLNZP is, well, what we have there. Okay, so now let's move on to the order of SLNZP. And this is actually done with the first isomorphism theorem. So let's define, well, not really define, but use the determinant function. And observe the determinant function goes from GLZP into UP. So that's the group of units mod P. So that's going to be 1, 2, 3, up to P minus 1, where multiplication is modulo P. And we know it goes into UP and not ZP because we know the determinant is non-zero given that we are in GLNZP. And again, we know that this is a homomorphism just from linear algebra. We know the determinant of A times B is the determinant of A times the determinant of B. And now let's observe that we have A is in the kernel of the determinant if and only if the determinant of A is equal to 1. That's because the identity over in UP is just the number 1. But that's if and only if our A was in SL in ZP. Okay, great. So that gives us this isomorphism using the first isomorphism theorem that GL in ZP mod SL in ZP is isomorphic to UP. And I guess we didn't check there that this homomorphism is surjective. I'll leave that as a bit of a homework exercise. But now if we take the order of everything in this isomorphism, we get the following equation. So we'll have the order of GL in ZP divided by the order of SL in ZP is equal to the order of UP. But the order of UP is, of course, P minus 1. So now solving for the order of SL in ZP will give us this second result. Okay, now let's move on. Okay, so now we're gonna fix the field to be just the real numbers, and we're also gonna look at the orthogonal group. And I should say here, the real orthogonal group. And you might say, well, why are we gonna look at the orthogonal group over R? Well, that's because, like I said before, our goal in the end of all of this is to look at so-called wallpaper groups, and you need to have some sort of knowledge of the orthogonal group to see that. Okay, so the orthogonal group is defined as follows. We'll say it's ON, and this is going to be all A in GLNR, so that if you take A times A transpose, you get the identity matrix. Observe that's the same thing as saying that A transpose is equal to A inverse. So let's look at the structure of O2. And the purpose of doing this is, again, because we're going to look at wallpaper groups. And looking at wallpaper groups means that we need to restrict everything to the plane, because wallpaper lives in the plane. And thus we'll need to look at O2. Okay, cool. So let's observe that if we have, well, I'll call our matrix A, which has got to be a 2 by 2 matrix, A, B, C, D, inside of O2, that means that, well, first of all, A transpose times A is equal to the identity matrix. But observe that means the following. So A transpose is going to be A, B, C, D, read column-wise, whereas A will be, let's see, A, B, C, D, read row-wise. But now we can take the product of those two matrices, and we'll have up here A squared plus C squared. Here we'll have AB plus CD. Down here we'll have another AB plus CD. And here we'll have B squared plus D squared. So we've got something like that going on. So in the end, let's observe that we've got a system of equations. So let's note that right here. We have A squared plus C squared is equal to 1. And we have B squared plus D squared is also equal to 1. That's because we want this to be the identity matrix, the matrix 1, 0, 0, 1. And then what else do we know? Well, we also know that AB plus CD must be equal to 0, because those are the off-diagonal elements. Okay, so let's see if we can massage these equations to get some more information. So I'm going to start by observing that this equation down here, the third, is the same thing as saying that AB is equal to negative CD. But now squaring this, I see that AB quantity squared is the same thing as CD quantity squared. Now what I'll do is I'll use that in the first equation. I'm going to do that by multiplying both sides of this first equation by B squared. So that's going to give me AB quantity squared plus BC squared is equal to B squared. But now I can replace that AB squared with CD squared. And now I'll write that as C squared D squared plus B squared C squared is equal to B squared. So we've got something like that going on now. Now, where can we go from there? Now, factoring a C squared out of this left-hand side will give us C squared, then reordering B squared plus D squared equals B squared. So in other words, we have B squared equals C squared, but now we can rewrite that as C equals plus minus B. Okay, nice. But now we can also play a similar game using the fact that B is plus minus C to get down to D is minus plus A. So what I mean by plus minus and minus plus, I mean that if we've got C is equal to positive B, then that means that D is equal to negative A, and vice versa. Okay, so let's see what we can do with this information. So summarizing all of that stuff we had on the last board, we see that the structure of O2 is the following. We've got matrices that are read row-wise, A minus B, B, A, or A, B, B minus A. And I should say with A squared plus B squared in both of these cases equaling 1, which we had that on the previous board as well. So now I'd like to observe that this second type here can be rewritten as the first type, A minus B, BA, times the matrix 0, 1, 0, negative 1. And so you can check that pretty easily. So that means that, well, we really have O2 is equal to the following. So it's going to be equal to matrices of the form A minus B, BA times the matrix 1, 0, 0, minus 1 to the, maybe for instance, K power. And this is where A and B are real numbers and they're non-zero. So I guess that's covered in the fact that A squared plus B squared equals 1. And we have K is either equal to 0 or 1. Of course, it's going to be 0 if we have this first type, and it's going to be 1 if we have that second type. But wait, there's more. And there's more because if we think about this A squared plus B squared living in the AB plane, and we have A squared plus B squared equals 1, that's parametrizing the unit circle. So that means that there exists some value theta on the interval from 0 to 2 pi, where A is equal to cosine theta and B is equal to sine of theta. Now, putting that into here, we have matrices of the following form. So we've got cosine theta minus sine theta, and then sine theta cosine theta, and then times 1, 0, 0, minus 1 to the K power. And now we can take theta on the interval from 0 to 2 pi. We don't need 2 pi because it's 2 pi periodic. And then we can take K to be equal to either 0 or 1. So the way to think about this is we've got a rotation matrix here, and we've got a simple reflection over here. And so in this way, the orthogonal group can be thought of as some sort of continuous generalization of the dihedral group. Notice we've got rotations and reflections. Okay, so now that we've got this structure of O2 sorted out, let's move on. So now we've got a bit of a classification of the orthogonal group, or orthogonal matrices. So let's say we've got an element A from GLNR, then the following are equivalent. So A is in the orthogonal group. It's an orthogonal matrix. The columns of A are an orthonormal basis of Rn. That might be something you saw in a linear algebra class. And then the inner product of AX with AY is simply XY. Here we're taking the inner product to be the standard dot product of Rn. Or we have the norm of AX minus AY is the same thing as the norm of X minus Y. Or finally, we have the norm of AX is the same thing as the norm of X. And those results over there are for all vectors X, Y, in Rn. Okay. So let's start with 1 implies 2. So let's suppose that we write A column-wise. So it's going to be vector v1, vector v2, all the way down vector vn, where these are all in vectors kind of going down. This is the standard way to do this. But now let's observe that means that the identity matrix, which is of course a diagonal matrix with all 1s, is equal to A transpose times A. Because being in the orthogonal group, which is what we are assuming, means that your transpose is your inverse. But taking the product of A transpose and A gives us something nice. So we could write A transpose as V1 transpose, V2 transpose, all the way down Vn transpose. And that's where now we're writing it row-wise. That's going to be multiplied into our A, which is written column-wise with the V's. But now let's observe that that gives us an n by n matrix. In this first entry, we have V1 transpose V1. And then here we're going to have V1 transpose V2, all the way down V1 transpose Vn. So that's our first row. Then our second row starts V2 transpose V1. The next one is V2 transpose V2. All the way down here, we've got Vn transpose Vn. Okay, cool. So you can fill in some of the more details if you want to, but I don't think it's strictly necessary here. I think the pattern is pretty clear. But let's recall how the inner product is related to this transpose times original vector kind of thing. And this, in fact, gives us the inner product of v1, v1 in this first entry, the inner product of v1, v2 in this second entry, all the way down the inner product of v1, vn in this last entry. Here we'll have inner product v2, v1. Here we'll have inner product v2, v2, so on and so forth. Down here we'll have inner product vn, vn. But observe, that's equal to the identity matrix. So that means the only thing that is non-zero is what's going on the diagonal, and in that case you're getting 1. But observe, that's exactly what it takes to have an orthonormal set of vectors. And since there are n such vectors, they form an orthonormal basis of Rn. And we could write that as vi vj, the inner product of vi vj is delta ij. Recall that that means that that's equal to 1 if I is equal to j and 0 otherwise. Okay, so there's the proof of 1 implies 2. Now let's move on to 2 implies 3. Okay, so now moving on to 2 implies 3, let's suppose we've got a matrix whose columns are an orthonormal basis of Rn. So in other words, we can write that matrix column-wise where the inner product acts like that. Okay, so now let's do the calculation over here for 3. So that's going to give us ax, a, y, so that's that inner product, but that's going to be x transpose, a transpose, or maybe let's not skip the step here. That's going to be ax quantity transpose times ay. But then the transpose switches the order of multiplication. That's going to give us x transpose, a transpose, a, y transpose. Or sorry, just y. And now you might say, well, a transpose a is the identity, but we're not assuming we're in ON here. But notice that this essentially does everything for us. We're going to have x transpose, and then here we have v1 transpose all the way down vn transpose. That's our matrix A transpose. And here we've got v1 all the way down vn, and then vector y. But if we take that product, we're going to get exactly the matrix of all of the inner products that we had before, which, since we're assuming an orthonormal basis here, that's just going to give us the identity matrix. So that means the identity matrix will essentially disappear, and we'll have x transpose y, which is the inner product of x with y. So there, we've established 3 using only 2. So now let's move on to 3 implies 4. Okay, so for 3 implies 4, we essentially just need to use the connection between the inner product and the norm. So let's look at the norm of ax minus ay. But since the norm is always positive, we don't lose any information by squaring it. I should say non-negative. Okay, but then we can factor the a out, and we'll have a times x minus y inside of the norm. That's just using the distributive rule of matrix multiplication and matrix addition. But now the norm of a vector is the same thing as, or the norm square of the vector is the same thing as the inner product of that vector with itself. So that's going to be a times x minus y inner producted with a times x minus y. So something like that. But now we can use number 3 to essentially disappear those a's, and we'll have the norm of x minus y with x minus y, or I should say the inner product of x minus y with itself, which is the norm squared of x minus y. And now, well, taking the square root of both sides essentially gets everything done here. Okay, so now let's look at 4 implies 5. Well, 4 implies 5 is almost immediate. You just have to set y equal to 0. So to be real thorough here, the norm of ax is the same thing as the norm of ax minus a times the 0 vector, which is the same thing as the norm of x minus the 0 vector, which is the same thing as the norm of x. So we're good to go there. And now let's do 5 implies 1. Okay, so let's assume that we know 5 is true, and then we want to show that A is an orthogonal vector. Or sorry, an orthogonal matrix. So observe, if 5 is true, then that means that we know 0 is the same thing as the norm of ax minus the norm of x. Just, subtracting a norm of x over. But now that's going to be the same thing as the inner product of ax with itself minus the inner product of x with itself, where I just realized I forgot my squares here. Okay, cool. But now what I can do is I can rewrite those inner products using transposes and such. And that's going to give us x transpose A times x minus x transpose times x equals 0. But now we can factor some stuff out and observe that means that x transpose times A transpose A minus the identity matrix times x is equal to 0. But that's true for all x. And since that's true for all x, that means this matrix here in the middle has to be the 0 matrix. But observe, that's the 0 matrix if and only if A transpose times A is equal to the identity. But if A transpose times A is the identity, that means that A transpose is A inverse, which means we are inside of the orthogonal group. Okay, so that completes our loop of equivalence. Okay, so now I'm going to leave you with some exercises. Okay, so I've got some exercises for you. So let's observe that SL2Z3 has 24 elements by our theorem that we proved. Notice that there are some groups that we know about that have 24 elements that are non-abelian. I think you can easily check this group as non-abelian. For example, S4 has 4 factorial or 24 elements. And D12 also has 24 elements. Now the question is to determine if SL2Z3 is isomorphic to either of these, or perhaps it's a so-called new group, new to us perhaps, that has 24 elements and is non-abelian. Now next up, let's find subgroups of GL2Z3 isomorphic to groups in the following list. So there's kind of a bit of work to do here, but this is not even all types of subgroups that are inside of GL2Z3. I think this is really interesting. GL2Z3 has a lot of structure to it. And then finally, let's say that A is in SL2R and V and W are in R2. Then what we want to do is show that the parallelogram defined by V and W has the same area as the parallelogram defined by AV and AW. And that's a good place to stop.